Hey, how are you doing, guys? I'm Dohan, who's in Expert 2, which is about object detection and multimodal head. So let's get started. These are the outlines. First of all, we are going to discuss what object detection is. Then we are going to grab our data and prepare it, building the model, and we will take a look at the loss functions that used in object detection. And finally, we will go through the multimodal head notebook. So let's get started. Let's get started with object detection. So object detection refers to the task of identifying and localizing objects within an image. It involves training a model to predict bounding boxes around objects of interest and classifying them into different categories. So this can be applied to a wide range of applications, including autonomous driving, robotics, facial recognition, and more. It enables machine to understand and interrupt visual data by detecting and recognizing objects of interest, which is crucial for many real-world computer vision tasks. So here we import Vision Library from fastai, and we are going to work with Pascal dataset. So the thing with bounding boxes is that most of times the label comes in Coco style JSON, and fastai has a very nice get annotations functions that we can use to grab the image and their bounding boxes. So here is the list of all the files that we have. Then we go ahead and call get annotations to the string JSON file. So if we take a look at the first image and the first bounding box label, we see the 4 points which is correlate to the bottom left and top right along with a particular class. Next, we want to be able to quickly look up a corresponding image to its label. So here we define a dictionary called image to bounding box. It uses a zip function to combine two lists, images, and label bounding box. So it maps each image in images to its corresponding set of bounding box and label bounding box list. And here we check the first item in our dictionary. So as you can see, here is our image and here is its corresponding set of bounding box along with the label. And now let's build our data block. So we will have two outputs, the bounding box itself and a label with one input. So we need to make some getters to get our outputs and the input. So here we define a list of three getters. Each getter function takes an input O, which is represent an image. So the first one returns the path to the image file, and the second two are going to search for that file name bounding box along with the label. Then we define our item transforms that resize the images to 128 by 128 using pad method. And then we define our batch transforms that include transformations such as random rotation, horizontal flipping, dihedral transformation, and normalization. And we need a custom get images because we want our images that come back to us, not the entire folder. So for this, we define getTrainImages function. So nope here says no matter what my input is, ignore it and just return a list of images. And here we make our data block where we have an input of image block and an output of bounding box block and bounding box label block. And we are going to use a random splitter to split our data. Then we define our custom get items, the getter, which is the three that we defined earlier. And then we pass it our item transforms and batch transforms and the number of inputs that we want. Then we build our data loaders. Then we assign it with some classes. And now we can show a batch of our data. For the architecture, we are going to use RetinaNet. It's the one that Jeremy lectured on the part 2, and here's the link. So here we import it. And we are still going to use transfer learning here by creating an encoder, which is the body of our model, and a head. So here we create a body and we are going to use a Resonance 34 architecture. And then we grab the number of classes. And now we can call RetinaNet architecture. We will pass in the encoder the number of classes and what we want our final bias to be on the last convolutional layer. So Jeremy has his example at -4. Let's take a look at what this RetinaNet is really making, because now we have multiple heads for one model, because this model is going to output from 2 to 3 different values. So if we look at the previous examples that we show in the previous videos, we just have one head that has a linear layer as the last layer. But here we have 3: smoother, classifier, and box regressor. So if we look at the smoothers layer, it's a whole bunch of convolutional 2D. And the classifier, it's still convolutional layers. And for box regressor is also convolutional layers. So there is no linear layer here, and the reason for that is all of the extraction of the key points and the labels happen in the forward function of our model. Now we can move on to our loss function. For RetinaNet to work, we need to define what the aspect ratios and scales of our image should be. So the paper used 1/3 to the power of 1 and 2, or 2/3 to the power of 2. But we are going to use -1/3 and -2/3 instead. So as you can see here, we define our aspect ratios and our scales. And we are going to use a loss function designed for RetinaNet called RetinaNet focal loss, pass it our scales and our aspect ratios. Now we are going to make our learner. So here we define a function called RetinaNet split. So the purpose of this function is to split a model into different components for training. So first it creates a list called L. This list containing several components of the model, including encoder, C5 top 6, P6 top 7, merges, smoothers, classifier, and box regressor. And then it applies the params function to each component in the list, which returns the trainable parameters of each component. So here we made our learner, passed the data loader, the architecture, the loss function, and our splitter function. Then we freeze our model. And now let's train it with 10 epochs. And here's our result. So let's go with the second notebook. Here we will cover how to build multimodal vision model for the Bengali AI competition. So let's take a look at Bengali AI. It's a Kaggle competition about classifying handwritten digits. So the goal of this competition is we are given one image of handwritten character and we need to extract 3 different things from it: the root, the vowel, and the consonant. So let's go through and look at how we do that. So here we download the dataset. The first issue is all of our data is stored away in CSV files. There is no image file, so we need to go through and generate it. So we will use a notebook in Kaggle to help us for doing this, and here's a link for that notebook. Let's open it. And here is the notebook that we are going to use. And the notebook that we are going to use here is used for generating 128 by 128 images. And the data is stored in 4 Parquet files, so we can read this into pandas. So here we go through and open all of our Parquet files. And here's our files. And here we clean our data by making some bounding boxes and then do some sort of crop resize. So after running this algorithm here, you can see this is our original image, and here it is after applying the algorithm. So as you notice, this is a 2D images. So we need to keep track of the mean and the standard deviation when we work with it. And from here, we want to generate the full data set and store it away in some sort of zip file. So this is what this code here is going to do. And here we calculate the mean and the standard deviation because we will use them for normalization. And now let's go through and look at how to build the data block for this dataset. So here we go through and extract the newly made dataset. And we are going to make use of fast.library, so this is a cool way to visualize our neural network. And out of the 3 CSV files that come with it, we just care about train.csv file here. So let's take a look at it. As you can see, we have image ID, grapheme root, vowel, consonant, and grapheme. So we just care about these 3. So first we need to know how many possible outcomes there can be. So we can do this by grabbing the .unique attribute. As you can see here, we made a vocabularies for grapheme, vowel, and consonant. And now we can generate our data blocks. So we need 1 image block for our input and 3 category blocks for our outputs. And then we define our 4 getters, so each of them is a column reader. And finally, we define our transforms, so we are going to do some augmentations along with normalization from the statistics that we made earlier. And here we put them all together. And we are going to use a batch size of 128. And for this dataset, because it's so big and takes so long to train, so we are going to train a very small sample of it, just 1000. And as you can see here, we define our data loaders. So if we show a batch of 1 image, as you can see here, we have our image and 3 individual labels. Now let's go with our heads because we have a model that does 3 tasks together. So the first thing is we are going to create a body of our model. As you can see here, we use a pre-trained ResNet 34. And the big issue here is ResNet was designed for 3-channel images, so we need to update the first convolutional layer to accept a single channel. So this is what this function here is going to do. Now let's go through and focus on the head. So there's some sort of helper functions using fast.library to visualize what we want our head to be. I want to go over this. It's kind of self-explanatory, especially whenever you go through and look at the examples in the documentation. But this is the type of the model head that we are going to build. So we will start with this convolutional 2D, and then we build three separate ones that have 168, 11, and 7, and the model output. And we will make it super simple and call it multimodal. So our multimodal is going to have a body that we are going to get the number of output features for, and then we are going to create three heads. And for the forward function here, so we get the output of the body and pass it through the three heads and just return them. And then we build the model, pass it the body along with our classes. And for training, we are going to borrow from Kaggle notebooks that we saw. So basically, we have a combination loss that's gonna work with a basic cross entropy loss, but has some weights associated with this. And then we are going to have some recall matrices that focus on the previous few predictions. And finally, we can make our learner and fit for 10 epochs. And here's our results. So that's it for today's video. Hope you enjoyed.